Thank you, Mohit, for giving us a brief about Longi. I'm Pawan Mathur. As Mathi has just said, I'm Pawan Mathur. I'm working as a technical manager in Longi Solar. And I was just going through some of the questions in the chat box, and I can say that majority of your questions will be answered during the course of this presentation. We have designed this presentation slides in such a way that majority of your questions like what's mono, what's the difference between mono and poly, and the efficiency and everything, all those questions will be answered, majority of them will be answered. So let's begin. So as Mohit has already spoken a lot about Longi, our company. Our company is into three parts. Into Longi Silicon, which is into manufacturing of mono ingot and mono wafer. Then we have a branch named Longi Solar, which is into the manufacturing of monocrystalline modules. And then we have a branch which is in China only, which is Longi Energy, which holds mono power plants. Particular reason why I'm again sharing the slides and these timeline details with you is that to tell you that we have extensive experience in the main heart of the solar module, that is the wafer, that is the cell. So we are a vertically integrated company. We were founded in 2000, and in 2020, we are doing extremely well as far as the module, every aspect of module is concerned. And we will see in the coming slides at how we are preparing. Right. Another thing which shows our dominance is that we have 40% global mono wafer capacity in year 2000. It has not changed much in 19 and 22. So the first thing that comes to your mind when you choose a panel is why mono? Why mono? And Longi Solar is a mono module manufacturer. So why only mono? Why you should go for mono? So let's go into the very basics. Now, right in front of you are the cell structures of two basic things. One is a monocrystalline module, one is a multicrystalline module. The cell structure of both the modules. So you can see that in left, in the monocrystalline module, there are no grain boundaries, whereas there are a lot of grain boundaries present in the multicrystalline module. Now, what is the problem with grain boundaries? These grain boundaries, they act as trapping centers for the charge carriers. The charge carrier finds it's much easier to move in a monocrystalline module, and that's why it has a better efficiency. Now, if I have to sum up, what are the major advantages of a monocrystalline module over a polycrystalline module? I'll sum up it as like the first thing, the first difference, major difference is the dislocation density. Now, the dislocation density is the number of dislocations in a unit volume, which are very less in mono and are comparatively higher in poly. So why this dislocation density is there, which is lesser in mono? That is because of the way the cell has been made, because of the manufacturing process. And that's the reason why I will discuss a little about the manufacturing process of the mono ingot and the poly ingot, because these differences between the mono and poly are directly related to the manufacturing process. The another thing is lesser iron impurities. I won't say that the mono doesn't have iron impurities. It has iron impurities, but the amount of iron impurities in mono are much lesser as compared to poly. The third thing is the carrier lifetime. The carrier lifetime is mono is much higher as compared to the poly. So because of these three defining factors, the mono always has a better efficiency. And efficiency is one thing which has to be taken care of really well when you are choosing a module for your rooftop application. So a better efficiency module will always be better while you choose a module for your rooftop application. So the reason why I have just given you the reason that why I want to discuss the manufacturing process of both the mono and the poly module. You see right in front of you, in the left side, there's a pipe-like structure, and then these granules. This is the feedstock for making both the mono and the polycrystalline module. Now I want to discuss a little about this granules, this basic structure, the polysilicon, how it is made, because this is the feedstock for both the mono and poly, and it is the treatment of these granules, the process difference, which makes a mono or a poly module. If we opt for the CZ process, we will have a mono ingot and a mono cell. And if we opt for the DSS process or the direct solidification process, then we find a polycrystalline cell. Right. So just to give you a brief how we get this feedstock, I just for the sake of your knowledge, right? Silicon, which is the most abundant material on this Mother Earth, that's something around 27%. That's highest after oxygen. Oxygen is 46%. Silicon is 27% on this Mother Earth. Now we have this silica is hidden in this form of silicon oxide. Now the material that we need for making solar cells is high efficiency silicon, that is electronic grade silicon. So how are we going to arrive at electronic grade silicon? So there are two major processes. First, we convert the silicon oxide into metallurgical grade silicon, which has efficiency of somewhat around 98%. And then this metallurgical grade silicon is converted into electronic grade silicon. So if we start the process, silicon is added with carbon or the sources of carbon like charcoal, coke, and they are put into an electrode arc furnace. And the temperature in that furnace is really high at 1800 degrees Celsius. The output which we have is a metallurgical grade silicon, efficiency of 98%. This metallurgical grade silicon is also utilized for manufacturing some of the lower quality solar cells after various chemical refinements. Now, to have a better efficiency in the cell, this metallurgical grade silicon is treated with anhydrous hydrogen chloride. So distillation is done and at 300 degrees Celsius, and the result is normally a silane product. And more often we get trichlorosilane. I mean, majorly the manufacturers use the process we get, the output we get is trichlorosilane. Now there is again a treatment of this thing, and in the Siemens bed reactor, eventually we get electronic grade silicon, which is the feedstock for both mono and poly module. So this is electronic grade silicon. Now we opt for the CZ process to make a mono wafer. So what is the CZ process? What we do is that we have a furnace. Now this furnace is also moving. In this furnace, we put the impurity of boron or gallium. I will discuss in coming slides that what impurity do we use to make a P-type wafer. And then we add this feedstock to it. Now, this furnace is heated up at a high temperature and it comes into molten form. So after that, from top side, a seed crystal is dropped, and normally, very slowly, the seed crystal is pulled up. Now what we get is this ingot. I have a very interesting video for you which will make the CZ process very clear to you. So this is the furnace in which we have added impurities and the feedstock. Now this thing is heated up and it comes in the molten form. Now what we do is, in the second step, is that we add seed crystal to it from the top side. Now this is the seed crystal which is coming down, and this seed crystal is slowly dipped and then taken up. So it is this process is done at various temperatures, and this churning is there, continuous churning is there. Slowly we are taking out this seed crystal, and eventually the temperature is also controlled, so we get this silicon ingot. So this is our final product of silicon ingot. And what we do, just to give you a brief idea, because somebody asked in the chat box that how we make this poly. So what we have is that we have big crucibles. in those crucibles, we add our polysilicon and the impurity of boron. Now we heat this square crucibles on a high temperature, then we allow it to cool down. After cooling, we get these square kind of shapes, and you can see it and you can observe it that because of the shape of the ingot, the shape of the cell is also different. If you are using a mono ingot, and if you want to draw a square out of it, then a lot of material will be wasted. So instead of making it a perfect square, we just show off the edges, and eventually we have this kind of octagonal kind of a structure, wherein in a polycrystalline ingot, multicrystalline ingot, it is already in square shape. So when we cut it, it remains in square shape. Now this this monocrystalline module with all monocrystalline wafer, with all the benefits that I stated earlier, it has low dislocation density, it has no grain boundaries. So no grain boundaries, lesser charge trapping centers, and as a result, a better efficiency. So again, this slide shows the basic difference between the making of a monocrystalline wafer and a polycrystalline wafer. We use the CZ process, then slicing is done, edges are shaved off, and we get a wafer of and a cell of mono. And if we just put this material into a crucible and then we make squares out of it, we'll get a polycrystalline module. Cell, sorry. So this is a brief about the products of Longi Solar. In May 2016, we came up with HIMO 1. It had the PERC technology, and it had lower degradation technology too. So we always had this advantage of better, lower degradation